All right, so as I mentioned in previous videos, we're going to need, if we're going to use this Krylov space method, these projection methods, we're going to need efficient ways to compute projections, okay? And not only that, we're going to be, like, our universe, remember I said in the previous video, we're sort of restricting our universe to this Krylov subspace. And so then we don't need to know how A acts on the entire gigantic n-dimensional space. We only need to know how A acts on this smaller subspace, and we want to analyze just A acting on this smaller subspace. Because solving, if we have a million unknowns, and we can kind of restrict ourselves to a subspace of dimension 100, that problem is much, much easier to solve than a similar problem on 1,000 than the 1,000 dimensional problem. So, sorry, the 1,000 dimensional problem. So that is the idea here. But we need a way to do computations efficiently to let us really take advantage of the fact that we're working in a smaller space. And also, we need to sort of build our subspaces in such a way that they're going to be going toward the solution. Anyways, so as we have seen, Km is going to be the subspace span. Sorry, it should be the span. That's what S means. R naught, AR naught, up to A M minus 1. R naught like this. Okay, and again, we need to come up with an efficient way to compute orthogonal projections onto this. Now, in general, if we have an orthonormal set Q1 to Qm, if this is an orthonormal basis for Km, then the projection, the orthogonal projection, can be given in the following formula here. The projection of a vector x onto this subspace is going to be equal to Q times Q transpose x, where Q is just, sorry, there should be no commas there. Q is the matrix whose columns are given by these orthonormal vectors Q1 through Q. Okay, and so we're going to need to be able to solve equations like, similar to this, Q transpose A Q Y is equal to something. The method, whatever is going to be there, is going to depend on the method. Now, as I said in the previous video, this turns out to not be a significantly easier problem than the one that we started with. So what we need to do then is we need an algorithm that is going to be similar to Gram-Schmidt in the sense that we can sort of, have a orthonormal basis created for this set, add a vector, orthonormalize that with respect to the previous ones, and now have an orthonormal base for the next subspace. So we need a sort of modified Gram-Schmidt algorithm that's going to do something like that. But what we want it to do is we need it to compute things efficiently, and this is exactly what the Arnoldi algorithm is going to give us. So what we're going to do for the Arnoldi algorithm, this is like the third time I've made this video, so I'm getting a little tongue-tied with some of the words here. Okay, so this is going to be the Arnoldi algorithm. Okay, so it's going to start with a vector R naught, which is supposed to represent the first residual. So you have some guess x naught. This is just going to be b minus ax naught. So we're going to start with some residual R naught. And what is the output? Actually, the setup is a little bit better if we say this. It's going to start with this. It's going to start. It's going to give us. We're going to start with a matrix Vm plus 1. this is going to be an n by n plus 1 matrix we're going to initialize to 0, all zeros, and then also matrix h bar sub m is going to be an m plus 1 by m matrix, and we're also going to initialize to 0. Okay. And this is especially how we're going to program this. Now, the indices get a little bit confusing here because if you are used to Gram-Schmidt, there's going to be a few different things with the indices that might throw you off and be what you're not exactly expecting. And also we have like Vm plus 1 is n by m plus 1, but hm bar is equal to this size. And at the end of the algorithm, we're going to get both a matrix called Vm plus 1 and a matrix called hm bar here. There's just two different indices going on, and that's just kind of how it works. So, all right, here's how the algorithm is going to work. Or not how the algorithm is going to work. Let me tell you what the algorithm is. So step 1, we're going to say that V1 is equal to R naught divided by its magnitude. And now the first column of, we're going to say the first column of V is V1. Okay, so like a very standard, this is a very standard thing that we would do in a procedure like this. It's exactly what we would do if we're using the Gram-Schmidt procedure to get a QR factorization for our matrix. Okay, step 2. Now, this is sort of the iterative loop here. So there's going to be 2 loops here. For j equals 1 to m, we're going to do the following. We're going to compute wj is going to be equal to avj. Now, in some sense, remember in the previous video I said that if we're just going to naively apply Gram-Schmidt, we would start with R naught, then look at AR naught and orthogonalize that with respect to the previous ones, then just take AR naught, multiply that by A to get A squared R naught, orthogonalize that with the previous ones using Gram-Schmidt and so on and so forth. But the problem with that is once we've done this a few times, like the thing that we're computing is going to be A to a power times R naught. And as we compute larger and larger powers of A, what's going to happen is that the eigenvectors that correspond to the largest eigenvalues, and in fact the largest eigenvalue, is going to start to dominate. And so if we had 100% precise arithmetic in a computer, this wouldn't be a problem. But with less precise arithmetic, very quickly what happens is that the vectors become, these vectors, R naught, AR naught, A squared R naught, so on and so forth, in the precision that we have in the computer, those vectors start to become more or less parallel to each other. And it's very numerically unstable to do Gram-Schmidt on a set of vectors that are becoming more and more parallel to each other. So that's one thing this method is going to avoid. The other thing that it gives us is an efficient way to compute the matrix A relative to the basis that it's going to give us. But I'll talk about that in just a moment. Okay, so the reason I mention that is because this thing here, AVJ, this is kind of like the j minus 1th power of A. This is kind of like A to the power of j minus 1 times R naught. That's essentially what's happening here. But since Vj is orthogonal to the vectors that came before it, we're not going to have this problem that we had of the largest eigenvector dominating. Okay, so we're going to compute this right here. Wj is equal to Avj. And then now we're going to have an inner loop for I equals 1 to j. We are going to form Hij. Hij is going to be equal to Wvi. Hij is going to be equal to W times the inner product of W with Vi. And then again, this is going to seem very similar, a very similar step in the Gram-Schmidt process. We're just going to subtract off the projection of wj onto the previous vectors. And we're going to have wj tilde is going to be equal to wj minus its projection onto the previous vector. So here, I equals 1 to j, h, ij, vi, like this, okay? And finally, 5, h, j plus 1, j is going to be the norm of wj tilde, and then, let me write this in a different color so it stands out a little bit. Wj is equal to wj tilde divided by its magnitude. Wj tilde. Okay, sorry about that. Vj is equal to wj tilde. Vj plus 1. The new vector vj plus 1 is going to be wj tilde divided by its magnitude. Okay. So let me make a few comments here. The vectors are orthonormal. The vectors are orthonormal. Why is that? Well, the normal just means they have magnitude 1, and that's exactly what we're doing here. We're taking wj and dividing it by its magnitude. So, we're taking wj tilde and dividing it by its magnitude. So therefore, they have magnitude 1. And by the way, all of these, I didn't mention it, but all of these magnitudes and inner products here are just the standard Euclidean inner product and magnitude and stuff like that. Okay, so this inner product right here is just the standard Euclidean inner product. Okay, why are they orthonormal? Well, notice vj plus 1 is just a multiple of wj tilde. What is wj tilde? Well, we're taking wj and subtracting off its projection onto the previous vectors. So therefore, it's going to be orthogonal to the previous vectors. So then wj plus 1 tilde is going to be orthogonal to the previous vectors, meaning vj plus 2 is going to be orthogonal to the previous vectors, and so on and so forth. That argument is essentially just the standard Gram-Schmidt argument to show that the vectors are orthonormal. 2, well, the matrix V, Vm plus 1 is going to be V1 through Vm, Vm, then Vm plus 1. And then Vm is going to be V1 through Vm. Since the vectors are orthonormal, then the projection onto the Krylov space, I thought I had the Krylov space written up here. The projection onto the Krylov space of X is just going to be Vm transpose X, and then, of course, the projection onto the n plus 1 would just be this Vm plus 1, Vm plus 1 transpose X. Okay, and then finally, if we look at Vm transpose Vm, this is the M by M identity matrix. Okay. Now, the very nice property here is the H matrix. So let's think about what the H matrix is. So we're setting it to be the 0 matrix. Okay, so all of the entries are 0 when we start this algorithm out. How do things get filled in? Well, let's think about what happens when j is equal to 1. Okay, for j is equal to 1, so that is we do this step, we compute this, now we're here. J is equal to 1. Okay, wj is going to be equal to avj. All right, what are the h's going to be? Well, for I equals 1 to j, so that's just going to be I equals 1 to 1. We can compute hji. So after the first step of the algorithm, what's going to happen here? I and j, there's going to be an entry here, and then hj plus 1j. So hj plus 1, 1. So j is equal to 1, okay? If j is equal to 1, it's going to be h2, 1. That's going to be whatever this is. So we're not going to have an entry here. But after the first step, after the first step of this outer loop, j is going to have, or h is going to have zeros here. We're going to have an entry here, an entry below the diagonal, and then zeros everywhere else. Okay, now what about here where j is equal to 2? Okay, let's think about what happens when j is equal to 2. Okay, so this is the outer loop. In the outer loop, if j is equal to 2, in the inner loop, I is going to be equal to 1 and 2. So we've got hij. So j is the column, so we're in the second column. And this says we're going to put entries in the first 2 rows in the inner loop. And then once we exit the inner loop, we're going to put an entry in j is equal to 2, h3, 2. So in other words, an entry like this, and zeros everywhere else. Okay, and so you can see what's going to happen. If I just do one more, we're going to go all the way down, we're not going to stop at the diagonal, we're going to go one below. And so what we have is a matrix, so h bar m, it's what's called, it is what is called an Hessenberg matrix. It is almost upper triangular. It's m plus 1 by m, and the k equals minus 1 diagonal. Okay, that's kind of like Python notation, or NumPy notation. The diagonal below the diagonal, everything above that is going to be equal to 0. So the k equals 1 diagonal below that is going to be equal to 0. Okay, so below the entries are 0. So below that diagonal, the entries are going to be equal to 0. So it's an almost upper triangular matrix. But notice what the entries of this are. The entries of the matrix, what is W? There should be WJ here. What is WJ? It's AVJ. So the entries of the matrix are going to be equal to A VJ VI. Okay, but all this is just the representation of the matrix according to the basis for Vm plus 1. That's what that tells us. Okay, and so what we can form then, we can make that formula. If you're not quite used to what that expression means, when I say that gives us that h, their h bar m is going to be a matrix for A relative to a basis. Let me just give you an explicit computation so that we can see what this means. So let's say that Z is in my space Km. So then I can write Z as a linear combination j equals 1 to m of the inner product Z Vj Vj. It just comes from the fact that the Vj's are an orthonormal basis. Okay, so then if I compute A times Z, I just multiply both sides of this equation by A, and the sum on the right-hand side is j equals 1 to m, and we're going to get Z Vj A Vj. Now I meant to tell you exactly what this is leading to here, but what we're going to show, our goal is to show that A times Vm is equal to Vm plus 1 times h bar Vm. Okay, that is what this computation is leading to. Okay, so how can we do that? Well, this is where the strength of the Arnoldi, one of the strengths of the Arnoldi method comes in. What is A times Vj? Well, look, we have a formula for it. Wj is AVJ. So if I look at this formula down here and solve it for Wj, it's going to be Wj tilde plus the sum I equals 1 to j of Hij Vi, like this. Now, what is Wj tilde? Wj tilde is simply Vj plus 1 times the corresponding H. So Wj tilde is H j plus 1 j times Vj plus 1. So this is Hj plus 1 j Vj plus 1. But this term here is exactly what you would get if you just plug in I is equal to j plus 1. So I can actually write this as one sum. And it's going to be the sum I equals 1 to j plus 1 Hij Vi. Okay, but it actually gets better than this. It actually gets better than this. Why? Let's think about what Hij is for I bigger than j plus 1. Remember, that means the row is now below, we're now below the subdiagonal. If I is bigger than j plus 1, we are below the subdiagonal. So actually, Hij is equal to 0 for I bigger than j plus 1. So in other words, I can just have this sum go all the way up. I can have this sum, let me make sure I'm going to do this right, go all the way up to m plus 1. Okay, now we can't stop it at m because j here ends at m, and this sum goes from I equals 1 to j plus 1. So I have to go all the way up to m plus 1. Okay, but whenever we have a sum like this, is a linear combination of vectors, we can always write a linear combination of vectors as matrix vector multiplication. And we can do that in this step as well. So notice what's happening here. This is Vi times this, V1, let me make sure I have this right. Yes, okay. For every fixed j, we have this sum right here. And so we can replace this sum here. Let me just write it in this way. We're going to have the matrix V1, Vm plus 1, and then times the vector Hj, got to make sure I'm changing the right thing. Okay, H1j all the way down to Hj plus 1j, and then H m plus 1j. Now these entries right here, below Hj plus 1j, are all going to be equal to 0. Okay. Breaking out a new, fresh piece of chalk here. Okay. I think I've gotten this down to as small as I can go. Maybe I'll go a little bit more. All right, but now notice what we can do here. This is just the Vm plus 1 matrix, and it's not depending on j, so we can move that to the outside. And I'm just going to call it Vm plus 1. Now on the inside, what are we going to have? We're going to have the sum j equals 1 to m z Vj times this vector here. And I'm just going to write it like this. Where again, the top entries are going to be whatever they are given by the formula, and the bottom entries are going to be equal to 0. Okay, but notice what we're doing here. This is a linear combination of these columns, of these vectors here. But these columns here, so we can write it as a matrix with vector multiplication. But what are these columns here? They're just the columns from the H matrix. So in other words, this right here can be written as H bar. I said from the H matrix, but I needed to say from the H bar matrix. H bar M times Z V1 all the way down to Z Vn. Okay, now if you are comfortable with various linear algebra things, then you will recognize this vector right here. This is simply the coordinates of the vector z relative to the basis given by v1 through vn. Okay, we're assuming that z is in Kn. So we can write z as vm times some vector in rm ym. We've done this many times before. So if I now over here replace z with vm ym, I'm going to do the following. Vm ym v1, and all the way down here is going to be equal to vm ym vm like this. Okay, but notice if I do the transpose, when I move it over here, let me go back to the white chalk, we're going to get ym vm transpose v1. Come down here, similar, we're going to have ym times vm transpose little vm. There should be an inner product bracket. Like this. Okay. Like this. But what's happening here? Vm transpose times v1. Well, again, the rows of vm are the columns of vm. So the rows of vm the rows of vm transpose are orthogonal to v1. So the first row, like if we compute what this is, the first entry is going to be the first row of vm dotted with v1. That is v1 dotted with v1. The second entry is going to be the second row of vm transpose dotted with v2. That is v2 dotted with v1, which is equal to 0. I think I said that a little bit wrong. Let me say that again. The second entry of this product is going to be the second row of vm transpose, which is v2, dotted with v1. But v1 and v2 are orthogonal. So that's going to be equal to 0. So what we get here then, this is going to be the vector e1. That is a vector with a 1 in the first position and zeros everywhere else. And down here, this is going to be equal to en. That is a vector with a 1 in the last position and zeros everywhere else. But all this is then, the inner product of ym and e1 is just the first entry of ym. The next one would be the inner product of ym and e2. That's just the second entry of ym all the way down here to the last entry. The inner product of ym with em is just the last entry of ym. So this is just ym. Okay, so notice what we have proven then. We have this formula. This is a sub z, or not a sub z. This is a times z. Whoops. But z is equal to vm ym. So we've got a times vm ym. And what do we have over here? It is vm plus 1 times hm bar times ym. Now this is true, ym is a generic vector. This is true for any ym in Rm, and so this tells us that a vm is equal to vm plus 1 times hm bar, which is exactly the thing that we are trying to prove. Okay, so that's good. Another formula that we have, we can if we take this formula here if you take this formula here and multiply on the left-hand side, let me try to find a different color. If I multiply on the left-hand side, and of course on the right-hand side, if I multiply over here by Vm transpose, and we track through what's going to happen here and kind of do very similar computations to what we did before, well, if we come back over here, we have the sum I equals 1 to j plus 1 h ij, and we had vi. If we multiply this by Vm transpose, okay, then what's going to happen is that the last entry is going to be equal to 0. And so what happens if we sort of go through a very similar procedure to what we did with this computation, we're going to get the following identity. We're going to get the identity that says the following, sorry. Vm transpose A Vm is going to be equal to H sub m. So what is H sub m? This is H bar m without the last row. So it's an m by m matrix. And as we will see, we are going to need to be able to compute that times various things. We're going to want to be able to solve that times something, that times a ym is equal to something, but we're going to replace it with our Hn here, which is a Hessenberg matrix, which has a much nicer form than this big matrix right there, or this dense matrix right here. This is a dense matrix. This is also a dense matrix as well, but it's almost upper triangular, which is something that's going to help us. It's an advantage that we can use in the solution to various problems. So these are the two formulas. If you look in the book, whatever proposition gives this algorithm, I've sort of proven the first formula. This formula here, I've told you to just go back and did what we did before to prove the first formula, but just multiply on the left-hand side by Vm transpose, and these formulas just fall out from that. Okay, so that is it for this video. In the next video, I'm going to show how we can use the Arnoldi method in the specific case of the full orthogonalization method.